Hello guys, hope all of you are well in this difficult situation. Welcome to my lecture series. Let me introduce myself first. I'm Rinki Bhaumik, Assistant Professor, Department of Physics, JIS College of Engineering. Today's lecture is for first year. For first year, the paper name is Physics 1 and the paper code is EH101. The name of the paper is Physics 1 and 3 credits. There will be 3 lectures per week. Total 36 number of lectures will be there for all of you. This is for BTech first year as I said. Now let me show you your syllabus. This is your syllabus. First, this is module 1. In module 1, there is waves and oscillation. In module 2, there is classical optics where we have to discuss about interference of light and diffraction of light. In module 3, there is quantum mechanics 1 where we'll discuss about quantum theory and quantum mechanics. In module 4, there is solid state physics 1 where we'll discuss about crystal structure and semiconductors. And in the last module, that is module 5, we'll discuss about modern optics where there is laser and fiber optics. So this is your syllabus and these are some books which is recommended for all of you. In my last class, we discussed about the SC, BCC and BFCC. How many atoms are there? What are the relation between R and A and so on. Now today we'll discuss about the packing fraction calculation. Though in my last class I already have introduced the formula of the atomic packing fraction, which was APF, that is atomic packing fraction, is equal to small n small v by capital V. This was the formula. Now first we'll do for SC. For simple cubic the relation was A equal to 2R, isn't it? Now this one we derived in my last class. Now small v equal to 4/3 pi into small r cube. This is the volume of each atom. Now why 4/3 r cube? Because the shape of the atom, shape of each atom is sphere. So what is the volume of that sphere? 4/3 pi r cube. What is capital V? This will be A cube because this is cubic unit cell. Now the length of each side is A. That means side cube, that is the formula of the unit cell since it is cubic unit cell. Now let's calculate the atomic packing fraction. For that, first APF will be equal to small n. Small n is the number of atoms. So therefore n equal to 1. So if we put it 1, and small v equal to 4/3 pi into r cube divided by a cube. So a equal to, already we know that 2r. So 1 into 4/3 pi r cube divided by 2r whole cube. If we do it, then what we are getting? 8. So if we do the full calculation, then the answer will be 0.52. That is 52%. 52% is the atomic value of the atomic packing fraction. Then what we can say, that 52% of that unit cell is occupied by the atoms. That means 48% is empty space. So this is for SC. Now if we go for BCC and FCC, let's see what we are getting. For BCC, the relation in our last class, as we got A equal to 4r by root 3. This is the relation between A and R. Now small v will be again same. Small v will be same, which is 4/3 pi r cube. Now capital V equal to a cube. Therefore APF is equal to, now here for BCC, small n equal to 2. So 2 into 4/3 pi into r cube divided by a cube. So a cube 2 into 4/3 pi r cube divided by a equal to 4r by root 3 whole cube. Now for BCC, if you do the calculation, then the answer will be 0.68. So therefore finally the answer will be 68%. So 68% of the unit cell is occupied by the atom. Therefore 32%, there will be 32% volume which will be empty. So this is about the BCC, means body centered cubic crystal. Now we'll go for face centered cubic crystal. For FCC, if we do here, for FCC, the relation is A equal to 2 root 2r and volume V equal to 4/3 pi r cube and capital V equal to a cube and n equal to 4. This is the expression of the relation between A and R. V equal to 4/3 r cube and capital V equal to a cube and n equal to 4. Now APF, atomic packing fraction, is equal to 4 into 4/3 pi r cube by A. A means 2 root 2 into r whole cube. So if we do this calculation, then ultimately we are getting 0.74. So the final answer is 74%. So thus we can get the value of the atomic packing fraction for these three cases. First, for SC, if we put all the expression and value, then the answer is 52%. For BCC, the answer is 68%. And for FCC, the answer is 74%. Now, this is about the atomic packing fraction calculation. Next, we'll start a very new topic, that is Miller indices. Miller indices, that is very new topic to all of you. Now, what is Miller indices? To write down the Miller indices, there are some basic rules. The first one is, it will be written in first bracket. So if you write it in second or third bracket, then will not give us a Miller indices. The second point is, there will be no comma between them. If you use any comma, then it will actually give us some another physical quantity. Okay, so that will not give us the Miller indices. The third point is, there must be some integer. There must be some integer. So if there is any fraction, then we can consider it not to be as Miller indices. This is the thing. So these are the basic rules. Now, HKL, this can be called as Miller indices, which must satisfy the relations, like must satisfy the conditions. That is, the first condition, it is written in first bracket. Second condition, there is no comma between them. Third condition, there is no integer between them. So that means we can tell them as Miller indices. Now, why we have to study Miller indices, or what are the physical significances of the Miller indices? For that, I have to draw a figure like a cube we have. Now, in my last class already we discussed about the crystallographic axis. Like, this is suppose your x, this is suppose your y, and this is suppose your z. Then x, y, z, these three axes are called crystallographic axis. Okay, so suppose this length is A, this length is B, this length is C. So ABC are three different lengths along x, y and z. Now, what is the relation between this ABC and HKL? Actually, H equal to 1, or we can say in another word that if PQ are P, Q, R, if this is the intersection point and HKL is the Miller indices, then the relation between these two is P equal to 1 by H. Now this will be actually A by H. Q will be B by K, and R will be C by M. Therefore, the relation between the intersection point and the Miller indices is P is to Q is to R is equal to 1 by H is to 1 by K is to 1 by L. So this the intersection point and the Miller indices. Means if we know the Miller indices and if we take the reciprocal, then we can get the corresponding intersection point, or the coordinate we can know from the Miller indices. Now there is a question. Suppose the coordinate is 2, 3, 2. If this is the coordinate, then what will be the Miller indices? In that case, we have to take the reciprocal, like half, 1/3, half. In that case, since as we know that Miller indices cannot be integer, but it has to be some integer, that's why it will be multiplied with 6. What is 6? 6 is the LCM of this denominator, 2, 3, 2. So therefore finally we are getting the answer as 3, 2, 3. So if 2, 3, 2 is the coordinate, then the corresponding Miller indices will be 3, 2, 3. This is the answer. Similarly, if we have some like 0, 0, 1, if this is the Miller indices, then what will be the coordinate? Obviously in that case again we have to take the reciprocal, like 1/0, 1/0, 1/1, and the answer is infinite, infinite, 1. So if 001 is the Miller indices, then the corresponding coordinate we are getting as the infinite, infinite, 1, that is your coordinate. Thus, if we go to the figure, in this figure, if we ask the value of the intersection point of any plane, suppose we are considering this front plane. So for this front plane, if we ask what is the coordinate or what is the position, in that case you have to mention the coordinate. So that's why we need to calculate the Miller indices. Now in another word we can say Miller indices is an identity of any plane. Okay, so it's an identity of any plane. So this is about the Miller indices. Now we have to implement it. Suppose first we have to draw the cube well. To show the planes well. This is the cube. Now you give the axis. This is your x, this is your y, and this is your z. X, y, z, three axes are there. Now 1, 0, 0, 1. This is the Miller indices. Then we have to find the corresponding coordinate. So the corresponding coordinate is infinite, infinite, 1. As we can see here, along x-axis the coordinate is infinite. Along y-axis the coordinate is infinite. Along z-axis it is 1. So in that case, between these 6 planes, which plane can have this coordinate, infinite, infinite 1. Which one can have this coordinate? Now, since this is unit cell, therefore this length is 1. This length is also 1 and this length is also 1. Therefore, this is since 1. So, if we consider this upper plane, this plane, as we can see, it is parallel with x-axis and also it is parallel with y-axis, but it lies at 1 on z-axis. Therefore, the coordinate is infinite, infinite 1. So, if we give a particular name, that is, suppose A, B, C, D, E, F, G and H. So, therefore, the name of the plane will be A, B, G into H. A, B, G, H is the answer. Next, 0, 1, 0. Therefore, the coordinate will be infinite, 1, infinite. So, if we go to the unit cell, what we are getting? If we go along y-axis, then this plane is parallel with z-axis. And this plane is parallel with x-axis also. But the intersection point here is 1. So, therefore, this plane can have the coordinate infinite, 1, infinite. So, the answer will be C, F, G, B. This is the answer. C, F, G, B is the answer. So, 0, 1, 0. Therefore, the corresponding coordinate infinite, 1, infinite. So, the answer is C, B, G, B. C, F, G, B. This is parallel with z-axis. This is parallel with x-axis. But the intersection point here is 1. That's why infinite, 1, infinite. This will be the answer. Next, if we go for the 1, 0, 0, then 1, infinite, infinite. So the answer will be, since 1, infinite, infinite, therefore the answer will be A, B, C, D, because A, B, C, D means A, B, C, D. So, since this one is parallel with z-axis and this one is parallel with y-axis, but the intersection point here is 1, therefore this will be the answer. 1, infinite, infinite. So, A, B, C, D is the plane which can have the Miller indices 1, 0, 0, but the coordinate is 1, infinite and infinite. Next, if we go for 1, 0, 1, then the corresponding coordinate is 1, infinite, 1. So, what will be the answer? You see, along x-axis it is 1, along y-axis it is 1. Now, if we join them, and take the parallel line, this imaginary plane which is passing through it, this is actually imaginary, which is passing through inside the unit cell, that is called, that will have the Miller indices 1, 0, 1 and coordinate 1, infinite, 1. So the answer will be nothing but AGFD. So the answer is AGFD. In this kind of case, we don't have to think too much, okay? We just have to join them and we have to take the parallel line, and this imaginary plane will be the answer. Next, if the question is 1, 1, 0, then the corresponding coordinate will be nothing but 1, 1, infinite. So along x-axis 1, along this is actually 1, 1, infinite. So along x-axis 1, along y-axis 1. So the answer will be A, DH, GF. DH, GF. This will be the answer. Next, it can be, you can also ask to find out 1, 1, 1. This is very easy because along 3 axes there will be 1, 1, 1. So if this is 1, this is 1, this is 1, and if we join them, and then we can get a triangle, that is DFH. So here the corresponding coordinate will be obviously 1, 1, 1, because if we take the reciprocal, then what we are getting, that 1 by 1, 1, 1 by 1, 1, and 1 by 1, 1. So 1, 1, 1. Therefore the answer is DHF. So this is the answer. So this is about the Miller indices, but by which what we came to know that if we know the Miller indices, then we can get the corresponding coordinate. So this is nothing but an identity of a plane. Okay, and it must be written in first bracket. Okay, there will be no comma between them, and if we take the reciprocal, we can get the corresponding coordinate. And so this is about the full Miller indices. And one more thing, if coordinate is given, then we have to take the reciprocal, and it will be multiplied with the LCM. So if we multiply it over here, then finally we are getting the Miller indices. So if you have any question, then please feel free to ask. So thank you for today.
So what are Miller indices? They are a set of whole numbers to represent a plane or a direction inside a single crystal. In many semiconductor processing steps, precise surface orientation is critical and directly affects the device's characteristics. We need a systematic way to represent different crystallographic planes and directions within a single crystal, and the Miller indices are for this purpose. This picture shows that single crystal silicon wafer surface is carefully aligned to lie in a specific crystallographic plane, and a flat cut is ground along the edge to identify a reference direction within the surface plane. The top surface is represented by its Miller indices 100, and the upward direction perpendicular to this plane is represented by its Miller indices 001. Then how do we get these Miller indices numbers? Here is a procedure for a crystallographic plane. In the next slide, we will talk about the procedure for a direction. We follow a very simple step-by-step procedure to get the Miller indices for a plane within a single crystal. First, we need a coordinate system, so we set up coordinate axes along the edges of the unit cell. In this simple cubic cell, it's the x, y, z axis. Then let's look at the plane of interest and write down the values where it intercepts the axis. For this example, it is A for x-axis, 1/2 of B for y-axis, and 3c for z-axis. Then we divide these values by the unit cell length along the respective axis. So A divided by A is 1 for x-axis, 1/2 of B divided by B is 1/2 for y-axis, and 3c divided by c is 3 for z-axis. Now we need to invert the values. So 1 over 1 is 1 for x-axis, 1 over 1/2 is 2 for y-axis, and 1 over 3 is 1/3 for z-axis. Then we multiply these numbers by a minimum possible integer, so these numbers become the smallest possible whole numbers. For this particular case, we need to multiply with the number 3, and we get 3, 6, 1 as the final numbers. Lastly, enclose this set of whole numbers inside a pair of curly brackets. So curly bracket 3, 6, 1 is the Miller indices for this plane. This picture shows more examples of Miller indices for different planes. There are two special cases we need to take care of. First, if the plane is parallel to an axis, the intercept along that axis is marked as infinity. When you invert infinity, you get the number 0. This is why you see zeros such as 1, 0, 0, which is parallel to y and z axis, 1, 1, 0, which is parallel to z axis, etc. Second, if the plane intercepts an axis in the negative portion, the minus sign is placed on top of the corresponding number, such as this -1, 0, 0 plane. The Miller indices for a direction are established by decomposing a vector in the direction into its components. Let's look at the 1, 2, 0 direction in this example. This vector's x-axis projection value is 1/2. Y-axis projection value is 1. Z-axis projection value is 0. We then multiply these numbers by 2, so the results will be a set of smallest possible whole numbers. Thus we get 1, 2, 0. We then enclose them inside a pair of square brackets. This is a convention for Miller indices of a direction. We take care of directions parallel to axis and negative numbers the same way as for planes as we pointed out in the last page. Lastly, here are some more direction examples and you can practice getting their Miller indices.